Hello everyone and welcome back to another video where we are going to be evaluating this nice integral right here. And actually a fun little fact before we get started, this is the integral that actually appears on the banner for the channel. So when I asked Maria to make it, she saw me attempting this problem. This was in like January. And yeah, bits and pieces of it ended up in the banner, which is so cool to me. But anyway, actually evaluating this. This is quite a fun one. And the first thing we're actually going to start by doing is multiplying the top and bottom by e to the minus nx. E to the minus nx. So that way, the denominator can then be expressed as, once I finish writing the entire rest of the integral right here, that way the denominator can be expressed as 1 plus e to the minus x to the n. And that's just so later on, we can express this bit right here as an infinite series. But what we're going to do next relies completely on what I did in a previous video. The reason I did that is so that I don't have to spend like 15 minutes here explaining it. I'm just going to invoke it and put a link in the description. Anyway, but that fact is namely that 1 over 1 plus e to the, or sorry, undo. 1 plus t times e to the minus x all to the n can actually be expressed as the n minus 1th derivative. It's always trying to say n minus 1th. Or n minus 1st. I don't know. This derivative of 1 over 1 plus t e to the minus x. Boop. And then, let me zoom out a little bit. But then because we're doing this, we do have a couple of extra factors, namely an e to the x times n minus 1, a negative 1 to the n minus 1, need more space, to the n minus 1, and then that's all over n minus 1 factorial. I will be using factorials and gammas sort of interchangeably, though it should be noted that this formula right here really, probably, only works for n being an integer, or it at least can't be, it can't be any fractional value because of this negative 1 term right here. But anyways, a little bit quirky there, I think. But anyway, what we can do is essentially substitute this fact right here in. And what we're going to do is just, well, we'll just take that and then put the derivative outside of the integral. So our integral becomes something quite long, but we'll simplify. So we have then the integral from 0 to infinity still of, alright, the x minus s times e to the minus nx here. And then I'll write all of our extra factors now in blue. So we have our e to the x n minus 1, negative 1 to the n minus 1 over n minus 1 factorial, and then times our derivative. So this to the n minus 1 of 1 over 1 plus t e to the minus x, and then our dx at the end. And when you look at this, this seems incredibly ugly, but you will notice, I mean, quite a number of things. First off, that these terms right here partially cancel. So whenever you distribute the x, you can cancel those right there. Secondly, again, as I said before, we can just move the derivative outside along with these terms right here. So our integral is actually just going to be, well, a derivative now actually, of an integral. So we have dn minus 1 over dt n minus 1 of, actually I'll put the constant outside the derivative just to make it look nicer. We have a negative 1 to the n minus 1 over n minus 1 factorial. Those are all our factors there. And then now inside of our derivative we have our integral. So the integral from 0 to infinity of x to the s minus 1 e to the minus x, e to the minus x, and then over this 1 plus t e to the minus x dx. And now what we're going to do, this is already quite messy, but we're going to express this term right here, our denominator, as an infinite series. And the reason we can do that is because this t e to the minus x term is always going to be, or at least in the limit, is less than 1. So, scrolling on down, we find, I should really get like more colors here actually. There we go. So we find that this bit right here can be expressed as an infinite sum. So we have negative 1 to the n minus 1 over n minus 1 factorial times dn minus 1 over dtn minus 1. Oh my gosh, it's a lot of writing, but that's okay. And then, yes, integral from 0 to infinity. It's a big integral, oh my gosh. X to the s minus 1 e to the minus x. We're just expressing this as a geometric series, I should say. Times, I'll put this term in pink, the sum from k equals 0 to infinity of negative t to the k, and then e to the minus kx, and then dx. And then one property of integrals and derivatives, for that matter, is that because the share, there's no k in that integral, right? So we can just move this outside, and it doesn't mess with the convergence. So I'm just going to reverse the order there. And just for the sake of brevity, I'm just going to draw an arrow down here. Just know that all that is still being applied. It's just a lot to write. So we still have our sum from k equals 0 to infinity. But now we have our integral, because this is the part we want to actually focus on and evaluate, times x to the s minus 1 e to the minus x k. So that's just minus x k plus 1 dx. And what we can do now is just do a quick substitution to evaluate this integral right here. So just let u equal x k plus 1, and du is going to be equal to dx, but we're going to have this extra k plus 1 term, so I'm going to stick that right here. So this means that our integral is just equal to, or well, this term right here in total is just equal to the sum. I shall move that up, pardon me. Is equal to the sum from k equals 0 to infinity of our integral from 0 to infinity still, but now we have our x to the s minus 1, but we can express x as u over k minus 1. So really it's a u to the s minus 1 over k plus 1 to the s minus 1 times e to the minus u, and then our du over k plus 1. But do note that we have k plus 1 times k plus 1 to the s minus 1, so we can just kind of erase that bit and erase negative 1, and we're good. And by properties of integrals again, we can just kind of throw that out, leaving us with the sum from k equals 0 to infinity of 1 over k plus 1 to the s, and then times the integral of u to the s minus 1 e to the minus u du. I'm not writing it because you might recognize that as just gamma of s, which is quite nice actually. So let's substitute everything back in to get something a bit nicer maybe. So what we have in total, I'm going to switch to a sort of yellow color now, is negative 1 to the n minus 1 over, I'm going to write gamma of n now, just so that we have everything in terms of gamma, gamma of n, and then in the numerator gamma of s, times our nth derivative right here. So actually, I'm going to write our sum first because we need to actually evaluate this derivative. So our sum from k equals 0 to infinity of 1 over k plus 1 to the s, but don't forget about this minus t to the k term right here, times minus t to the k, and then we're going to be differentiating that. Actually, I'll slide that on in here. d over dt, n minus 1, n minus 1, negative t to the k. So, this is what we have. And this is quite something, to be honest. But we are getting there. So to evaluate this, what we're going to do is just rely on the definition of like a falling factorial, essentially. So the first thing I'm going to do with just evaluating this bit right here is note that we can just take out the negative 1 to the k to avoid having to do any chain rule, and what we're left with is d over dt n minus 1 of t to the k. And now this term right here can be expressed then as k, and then the following factorial with n minus 1. With n minus 1 right there. And what I'm going to do now is just rewrite our summation as that. So what we have then is negative 1 to the n minus 1 times gamma of s over gamma of n. I wrote it differently. It kind of looks cool like that. And then our sum from k equals 0 to infinity of 1 over k plus 1 to the s, but then with the numerator we also have a negative 1 to the k. And then times k n minus 1, where that is the falling factorial right there. It's the notation Wikipedia uses. So this right here is sort of, in a way, our answer. In that we can... That's really not a plus, is it? My goodness, I can't write today. I do apologize. Again, this right here is sort of our answer in a way. If you type this into Desmos, I mean Desmos doesn't have anything for the falling factorial, but you can evaluate that. But if you plug this into Desmos, you would get a number. But there are just a couple of sort of constraints here. Again, n has to be an integer. But we could stop here, but that wouldn't be very fun, because you'll notice we have this negative 1 to the k, that's k plus 1 term, all to the s, and that right there is the eta function, but it's not, because we have that little pesky term right there. So what I'm going to do is just sort of, we could stop here again, but I'm going to sort of go a little bit further and evaluate this falling factorial in terms of some other functions, namely factorials, and, well, we'll see. So, what we're going to do is, well, expand this term right here. This falling factorial, this, actually, I do apologize. I'm going to re-index my series first, so we can express this as the sum from k equals 1 to infinity of negative 1 to the k minus 1 over k to the s, and then we have our k minus 1, n minus 1. Okay, sorry, I just want to get that out of the way. Now then, we can evaluate that. We could have done it before, but I just wanted to do that first to get it out of the way. So this falling factorial is essentially, well, by definition, it is equal to k minus 1 factorial over this number minus that number. So that's just k minus n factorial. And this right here actually has quite a few interesting things about it, because of, let me zoom in and kind of write this off to the side. If we say choose an n, right? Say we say, I don't know, say let n be equal to, I don't know, 3. What we have is, in the denominator then, is we have a k minus 3 factorial, and then numerator we still have our k minus 1 factorial. But you'll notice that these are both factorials, and they both have integers. So if we rely on the fact that k minus 1 factorial can just be expressed as, well, k minus 1 times k minus 2 times k minus 3 factorial, then these terms right here just cancel, and we're left with this k minus 1 and then k minus 2. So this might lead you to think, rightfully so, that, well, what if we could just express all of this in terms of, say, some polynomial, right? And that's where a thing called Stirling numbers of the first kind come in, expressed as, like, in general, like s of m comma n, where those are not the same as anything related to the problem, so I shouldn't write it as that. But basically, one way we can actually rewrite this following factorial, because of this cancellation, is actually as a sum, or a polynomial whose coefficients are the Stirling numbers. And namely, the way we do this is, say, we're going to have a sum from j equals 0 to n minus 1, sorry. The reason it's n minus 1 is just because of that right there. N minus 1. And then we're going to have our Stirling numbers, n minus 1, comma j. And then times, in Wikipedia it's x, but our x in this case is actually just going to be the argument of our following factorial, or one of them at least, namely that one. So it's actually just going to be k minus 1 to the j. Sorry, in my notes I have the general stuff written down. But this is actually one way we can express the following factorial. And one thing you might note is that a property of sums is that you can, if they don't have any common terms, so for example, there's no k in there, you can just reverse the order of the sum, meaning that this whole big sum involving this eta-esque function can actually just be expressed as the sum from k equals 1 to infinity of the sum, but I'm just going to put this on the outside actually, j equals 0 to n minus 1, of our Stirling numbers of the first kind, times k minus 1 to the j, and then we're going to have our negative 1 to the k minus 1 over k to the s. And we're really close. We are really close to being able to express this, like, in general, in terms of eta. The only thing that's stopping us is that this right here is a pesky little k minus 1 instead of just a k. But one way we can actually get around that is, for example, the binomial theorem. And applying this, we actually find that we're going to have another sum, but we're going to be getting rid of one. So we're just going to be left with 2 sums still, which is, I mean, kind of terrible, but we'll be able to express this in terms of eta anyway. So I think it's worth it. Anyway, but note that this is being raised to, I should really write this off to the side, the binomial theorem. So in general, if we have sum x plus y, sum j, this is equal to the sum from, say, L equals 0 to j of x to the j, apologies. There's my marker. X to the j minus L, y to the L, and then j choose L. And actually, one thing that can be noted is that you can swap x and y and just swap those things in the exponent, and it does remain the same. So what we have then is we have our x is just k and our y is -1, which leaves us with, well, our j in this case is, well, just j. That's the reason I wrote it like that. So we have j choose L, and then I'm going to say, in this case, our k is going to be raised to the, L power. And then we have -1 to the j, that's not a j, j minus L power. So that's our binomial thing taken care of, but then we also have to remember that we also have our Stirling numbers right here of n minus 1 comma j. And then we also have our -1 to the k minus 1 over k to the s, and then we also have our sum with k out there. So this is a lot, but if we rearrange the order of the sum again, we find that our sum from j equals 0 to n minus 1 of our sum of L equals 0 to j, well, all this, except for this right here, which we're going to absorb into this k right here, stays the same. So we still have our j, L, and then our -1 to the j minus L, Stirling numbers of n minus 1, j, and then we're going to have our sum with -1 to the k minus 1 over k to the s minus L. But this right here we can just, finally, express as the eta function. So, namely, eta of s minus L. So, what we can do is take this and substitute it in for, where is it? This up here. Actually, what I'm going to do is just yoink that, copy, and oh no, okay. Boop boop ba-doo. Off to the side. So this right here then can be expressed as this. We just have to throw in our -1 to the n minus 1, our gamma of s over gamma of n. And that right there, ladies and gentlemen, is the answer with Stirling numbers and everything else. That should be a j minus L actually. Why is that? Why did I write that as a 1? That's just weird. Okay. Boop. There we go. Okay. Actually, let's maybe evaluate. I'll save the evaluation for another video. It's gone on long enough. Thank you all for watching. This is gonna take long enough to upload. If you made it this far, congratulations! Yay! Thank you. I should really make T-shirts saying that you listen to all of this. But anyway, hope you all enjoyed. And I'll see y'all in the next one.